Hi, this is Mrs. Tempest, and right now we're going to learn about balancing chemical equations. So you should have previously learned how to write word equations and how to write skeleton or formula equations, and this is the last step, and it's called balancing. So suppose that we set up an experiment like the one below. After reacting the contents in the test tube with the contents in the flask, so it looks like we have calcium chloride in the test tube and we have sodium sulfate as our solution outside of that. And to react them together, basically we're just going to carefully tip over our flask and we're going to have that calcium chloride go into the sodium sulfate solution. So question is, what will happen to the final mass of the products? So knowing that we have these chemicals and the atoms that comprise them inside of the flask, this flask has a top on it, so that means that nothing's going to be getting out. So what would you assume would be the final mass of the products? So with this, we started off with 300.23 grams of reactants, and you can probably assume that since nothing is escaping, we're going to end up, after everything has reacted, with 300.23 grams of product. And this is going to lead into what we call the conservation of mass. So the conservation of mass states that mass cannot be created nor destroyed in a chemical reaction. It's like the conservation of matter, which states that matter cannot be created nor destroyed in a chemical reaction. So the mass has to remain the same before and after the reaction. And knowing that, we can assume that the atoms in a chemical reaction also have to be the same before and after a chemical reaction. So remember that we learned that atoms have different masses depending on what the element is. So if the mass has to be the same before and after the reaction, that means that whatever atoms we have in the beginning before the reaction have to be present in the product and after the reaction. All right, so the first example that we're going to go through should seem pretty familiar to you. So remember that when we are talking about atoms, those subscripts that are with the element symbol are going to tell us how many atoms are present. So with hydrogen and oxygen, those are going to react and form water. So in our skeleton equation, we have 2 atoms of each element on the reactant side. So I have 2 hydrogens and 2 oxygens. But on the product side, we only have 1 atom of oxygen and we have 2 atoms of hydrogen. So in order to show the conservation of mass, remember that the mass has to be the same on both sides of the chemical equation. Or you have to think the atoms have to be the same and the number and the kind have to be the same on both sides of the equation. So we have to balance the equation. Now you might be looking at this and thinking to yourself, okay, I need 2 oxygens. Why don't I just add a 2 to the end of my H2O? And then I will have 2 hydrogens and 2 oxygens on each side. This is something you can never ever do. You cannot change the subscripts because that is going to completely change what the substance is. And you don't have that kind of power. So if I am forming water, water has to have the equation H2O. If I ended up putting a 2 at the end of that, I no longer have water. I have hydrogen peroxide, which is very different than water. If you drink hydrogen peroxide, you're going to probably barf or die. If you drink water, it's going to help you live. So we have to make sure that in order to balance our chemical equation, we have to change what we call coefficients. And this is going to represent the number of molecules or formula units in the reaction. These coefficients are going to be larger numbers than the subscripts, and they're going to go before the substance in a chemical reaction. And what these coefficients do is multiply the number of atoms in all of the elements of that substance it's in front of. So let's look at a couple examples. All right, so if I just wanted to sketch out hydrogen and oxygen, so I'll have hydrogen and oxygen, and then H2O is going to be one oxygen with two hydrogens. All right, we have to determine how we're going to get two oxygens on both sides of our reaction. So right now we have two on the reactant side, but only one on the product side. Now the only thing I can do is add the same molecule of your reactants or products. So if I have two oxygens on the reactant side and I need two on the products, the only thing I can really do is add another water molecule to give me another oxygen. Remember that these are the oxygens and these are the hydrogens. All right, so instead of the one molecule of water, I now have two molecules of water. So I would put a coefficient of 2 in front of my H2O. Now you might notice that when I do that, my oxygens, I have the same on both sides of my reaction, but by adding that water molecule, it also affected how many hydrogens I have on the product side now. So over on the product side, I did have 2 here, but now I have 4 hydrogens. So to balance out the hydrogens on the other side, what I can do is add another hydrogen molecule, and that will give me 4 hydrogens. I put a 2 coefficient in front of here. So now you can see that we have 4 hydrogens on the reactant and the product side, and 2 oxygens on the reactant and the product side. And since it is equal on the reactants and product side, that tells us that we balance the equation and we are done. Here are just a couple reminders with counting atoms. So with subscripts, they're going to belong to the element in front of them. So if I have something like MgBr2, magnesium bromide, the 2 is only applying to the number of bromines in this substance. So if I'm looking here, I have 1 magnesium and 2 bromines. The subscripts outside of parentheses apply to all the elements within the parentheses, and they multiply the other subscripts within the parentheses. That was a mouthful. All right, so any subscripts outside the parentheses are going to be like the distributive product or the distributive property in math. So this 3 is going to apply to the sulfur, but it's also going to apply to the oxygen. Now I only have 1 sulfur here, so 3 times 1, I would have 3 sulfurs, and then I have 4 oxygens in each sulfate ion, so 3 times 4 would give me 12 oxygens. And notice that that 3 doesn't apply to the iron because the iron is outside of the parentheses. So we only have 2 iron based on this subscript. And last, the coefficients, which is something new, is going to multiply all the elements within the substance. So if I put a 2 coefficient in front of MgBr2, that's now saying that the 2 applies to both of the elements in my substance. So it has to apply to both of them. So that means that now I have 2 magnesiums, and then I have 2 times 2, which is 4 bromines. So the coefficients will multiply these subscripts to tell us how many atoms of this particular element we have. Now, balancing is something that you do need practice with. So just a couple balancing rules before we get some practice in. So the number and kinds of atoms on both sides of the arrow, we talked about this, have to be the same. And that's, remember, due to the conservation of mass. We have to make sure that what we start with, atoms and mass-wise, is what we end with. We're going to change coefficients to balance atoms. We cannot change subscripts. Remember, H2O is not going to be the same thing as hydrogen peroxide. Some find it easy to use the minnow approach to balancing and do so in this order. So this is one way that people have found it to be a little bit easier to balance equations. Basically, you're going to start with the metals and then move on to polyatomic ions, then balance out your nonmetals, then oxygen, and last hydrogen. I personally like to start with polyatomics if I can, if they're the same on both sides of the equation. I'll show you a couple examples of how I think about those, but really you need to practice and do what is easiest for you. This is going to require practice. Some might seem easy and some might seem hard. Don't give up on yourself. You need to have 2 carbon. All right, so sometimes people find it easier to split your equation down the middle. And basically this is going to split up the reactants and the products so that we can individually go through each substance that's in our reactants or our products, or each element. So basically with this, I'm going to just kind of list out the different parts of my reactants. So I have aluminum, I have copper, and then SO4, remember, is the sulfate ion. Since I have SO4 over here, I'm going to keep those together instead of separating out the sulfur and the oxygen, because it's going to be easier for me. So on the left, on the reactant side, what we're starting with, we have just 1 aluminum, and I know that because I don't have a subscript here, so that tells me I have 1 of them. I also have 1 copper, and then thinking of SO4 as an ion, since I don't have any parentheses or subscripts next to it, I only have 1 SO4. All right, we'll do the same thing on the other side. So aluminum this time has 2. Copper, I only have 1 again. And then SO4 this time, I'm going to have 3 of those SO4 groups. So SO4 I will have 3 of. Now, as I said, I like to start with the polyatomic ions just because I think it's easiest. So with that being said, if I have 3 sulfates on the product side over here, I need to balance that out on the reactant side. So I cannot stick a 3 at the end of my CuSO4 to show that I have 3. I have to make sure I put it in as a coefficient. Now, when I put a 3 coefficient here, remember it's going to multiply everything in that substance. So now I have 3 SO4s, but I also have 3 coppers. Now that's going to throw off my coppers on the product side, because remember I only have 1 over there. This one's pretty easy though, because copper is by itself. So the way that I can get 3 coppers is by putting a 3 coefficient in front, because remember that my coefficient multiplies by my subscript. So 3 times 1 is going to be 3. So right now I have my sulfates and my coppers balanced. However, my aluminum has to be balanced on the reactant side. Again, aluminum is by itself in this problem, so I can easily put a 2 coefficient on the reactant side so that my aluminums balance on each side. So now for this, I have 2 aluminums, 3 coppers, and 3 sulfates on each side of my equation. Double check to make sure, and then that tells me that I'm done. With the next one, you have a specific way of using that minnow process on your note sheet. I do things a little bit differently, so I'm going to show you my trick for doing something like this next one. So anytime that we have a hydrocarbon reacting with oxygen, I personally have found that it's easiest to look at my hydrocarbon, so my carbon with my hydrogen, and see if the number, if I divide my hydrogens by 2, if that's an even number or an odd number. If it's an even number, I generally leave my C2H6. However, if it's an odd number, so 6 divided by 2 equals 3, which is odd, I'm going to multiply this whole thing by 2. So my hydrocarbon gets multiplied by 2, and then I'm going to balance out my carbons and my hydrogens first before I do my oxygens. So right now, this 2 in front, this coefficient, multiplies by my 2 carbons. So I have 4 carbons on the reactant side, which means that I need 4 on the product side. So to see here, I only have 1 carbon on the product side, so I need to put a subscript of 4 in front of this. All right, when I do that, keep in mind that you're also changing how many oxygens you have, but we're going to save that for last. On the reactant side here, I have 6 hydrogens multiplied by 2, which gives me 12 hydrogens. On the product side, I only have 2 hydrogens, so to get to 12, I'm going to have to multiply this by 6. All right, so now that we have our hydrogens and our carbons balanced, the last thing to do is to add up all of my oxygens. So with my CO2, I have 4 times 2 oxygens, which is 8, and I'm going to add that to my 6 oxygens from the water. Now that's going to give me 14, which is divisible by 2, so it's going to make my reactants pretty easy to determine how many oxygen molecules I need. So 14 I need. I have 2 on the reactant side already, so I have to multiply this by 7 in order to get to 14 oxygens. All right, the last example, again, we're going to look at my polyatomic ions. So I have polyatomic ions, sulfate and nitrate. And it looks like I have them both on the product side, so I can do my little trick here. So as I said, I like to start off with balancing your polyatomic ions. So on the left over here with K2SO4, we have 1 sulfate, and on the right with barium sulfate, we also have 1. So I don't have to worry about those. If I look at my nitrates, however, here I have 2 nitrates, but over here, I just pretty much just have the 1 because I don't have any parentheses or subscripts next to it. So in order to balance this one, I'm going to put a 2 coefficient in front of my KNO3. When I do that now, I have 2 nitrates, but I also have 2 potassiums. Luckily for us, I also have 2 potassiums on the reactant side. So that is balanced. So my potassiums are good. My nitrates are good. Now for my sulfates, we already said that those were good and they have not changed. Last thing to check is barium. So here on the reactant side, I have 1 barium, and on the product side, I also have 1. So those check out as well. So with balancing chemical equations, you'll find that some are easier than others. Don't give up. Try your hardest. Try different things. Trial and error is going to be really important, and just kind of figuring out how your brain works is going to be pretty important with balancing chemical equations. If you have any questions, make sure to ask your teachers.